Hello, honors chemistry students. Today I would like to examine a rather large element or atom on the periodic table as we continue our review of atomic structure and quantum mechanics. The atom that I would like to look at today is that for lead, which has an atomic number of 82, and it has a mass number of 208. So this particular isotope of lead is a fairly large atom. Keep in mind that 82 represents the Z value, which is the atomic number, which is equal to the number of protons, which equals the number of electrons, and in this case, lead should have 82 protons and 82 electrons in a neutral atom. Similarly, 208 represents the A value, which is the mass number, which is equal to the sum of the protons, which are positively charged, plus the number of neutrons, which are neutrally charged. We've already established that there are 82 protons in this particular isotope, and to determine the number of neutrons, you would need to subtract the atomic number from the mass number, and you get a value of 126. 126 plus 82 equals 208. So that being said, we identify this particular isotope of lead as Lead-208 by its mass number. Lead is pretty far down on the periodic table. It's strategically positioned in row 6 of the periodic table, which is also known as period 6, because it has enough electrons to start filling the 6th energy level. We say it's strategically positioned in column 14, which is also known as group 4A, thus because the A elements are the representative elements. We say that the Roman numeral represents the number of valence electrons. Also, lead appears in the carbon family. It is in the same column as the carbon family of elements, all of which have 4 valence electrons, which would include silicon, germanium, tin, and lead. That being said, I would like you to construct an AELD diagram, or atomic energy level diagram. You're going to need a fair amount of space to do this, and I don't want to take up too much space because I don't want to get too far down on my sheet of paper here. Otherwise, we're going to lose the construction of this from the camera's view. Lead has 82 protons, and it has 126 neutrons. 82 and 126 sums to 208. We have the daunting task of placing 82 electrons. As always, you start on the first energy level. The first energy level is the n equals 1 energy level, or the K shell. Once the first energy level is filled, you move to the second energy level and put 2 electrons in an S sublevel on the second energy level. Then you start to fill the P's by Hund's rule. Each orbital in a sublevel gets 1 electron before you pair them up. So we now have safely represented 10 electrons, and we're up to essentially neon's location on the periodic table. Once the second energy level is filled, we move to the third energy level and place 2 electrons in the 3s. That would be the same for sodium and magnesium. And then we're going to move to the 3p, which would be similar to aluminum, silicon, phosphorus that we've already studied, sulfur that we've already studied, chlorine that we've already studied, and argon, which is a noble gas. So now we have placed 8 electrons on the third energy level, but it's important to note that the third energy level is not filled because the third energy level actually possesses 18 total electrons, and we have only placed 8. And this is the N equals 3KLM shell. Next, theory says we place the next 2 electrons on the 4s sublevel, which would be like potassium and calcium. And interestingly enough, before we start to fill the 4p's, theory says we go back to the 3rd energy level, and I want you to place these electrons for the D's in quadrant 1, so to speak. And we would say there's 1 electron in a 3D sublevel. I take back, let me correct that. There are 10 electrons in a 3D sublevel. So that takes us from scandium to zinc on the periodic table. That being said, once the 3D is filled, the 3rd energy level has its full complement of electrons, 2 in the s, 6 in the p's, and 10 in the 3Ds. Next, we move on to the 4p's, which would include the elements from gallium to krypton. So by Hund's rule, once again, we're going to place 1 electron in each orbital of a sublevel before we pair them up. So now we've started the filling of the 4th energy level. We have a total of 8 on the 4th energy level, which is the N equals 4 or N shell. Once we fill the 4p, we are at krypton, so to speak, on the periodic table. And our next move is to place 2 electrons on the 5s sublevel. Those would be similar to the ones for rubidium and strontium. Just like in the 3D, before we can fill the 5p, we have to go and place 10 electrons in the 4D. And those 10 electrons would be those for yttrium through cadmium. Once we're at cadmium and we've filled our 4D, and remember the 4th is not yet filled, we have a total of 18 on the 4th energy level, but it actually holds 32, so it's not yet filled. We move to the 4p, and by placing an electron, we move to the 5p by placing, 5p, by placing an electron there. Now we are at indium, 10, antimony, tellurium, iodine, and xenon. So now we have started to fill the 5th energy level, and we have 8 electrons in the 5th energy level. So this would be the N equals 5 or N shell. And you can follow along with me on the periodic table. Once we get to the 5p, we're at where xenon on the periodic table. So that being said, our next move is to place 2 electrons in the 6s. Those would be similar to cesium and barium. And now, interestingly enough, we reach a point on the periodic table that once you've filled the 6s, you need to drop back down 2 energy levels. So this is the 6, the 5, the 4, and we're actually going to place 14 electrons in what's called the 4f. So now, by doing so, we've included the electrons for cerium through lutetium. And in essence, we've filled the 4th energy level, because now the 4th has 2 in the s, it's got 6 in the p's, it's got 10 in the d's, and 14's in the f sublevel. So therefore that totals to 32. Once we've filled the 4f, theory says we then go and fill the 5d, which takes us from lanthanum all the way over to mercury. So once again, we're going to place 10 electrons on the 5D. Gets a little bit crazy, right? Once we've placed those electrons in the 5D, then we can place one electron in the 6P, which would be that for thallium, and then finally for lead. So we have really begun filling the 6th energy level, and you notice how, in a way, the 6th energy level is closer to the 5th energy level. N equals 6 would be KLMN. Whoa, KLMN. This should have been an O, and this should be a P. Sorry about that. So we're now at the P shell, or the 6th energy level. But note that lead has 4 valence electrons, 2 in the 6s and 1 in each of the Ps. So with that, you begin to see that all the S electrons are positioned to the right of the nucleus, and the P electrons are positioned above, to the left, and below the nucleus. The next thing I want you to do is to draw the electron dot representation. And the electron dot representation only represents the electrons in the highest occupied S and P. So therefore we would have lead, the symbol for lead, with 2 dots and an S and 1 in each of the Ps. We'll move on to orbital notation, and we're going to need just a little bit of space, and I may actually use a ruler here. So I'm going to kind of cheat and give myself as much space as I can afford to give myself. So we're going to use orbital notation to account for the placement of electrons and the energy levels. So if you'll bear with me, this is going to be a long, plot here. So I'm going to need plenty of room on the X and the Y axis. Keep in mind that energy is increasing as we move from the nucleus away by the, if you remember, Aufbau principle. So in orbital notation, you redo this, principle, almost misspelled that. All right, oops, sorry about that, but this is the Aufbau principle, which means to build up. So we build electron configurations from the bottom up, from closest to the nucleus to farthest away. So we recognize that the first 2 electrons go in a 1s. Once the 1s is completed, we then move to the 2nd energy level, which has a 2s, and it also has a 2p. I'm flattening this out just a little bit so I can make certain that when I get to the end of the diagram or notation, I have enough room. I'm going to place 1 electron going up in each of the orbitals of the 2p sublevel by Hund's rule. Once we've finished filling the 1st and 2nd energy levels, then we move to the 3rd. Keeping in mind that the 3rd has a 3s, it has a 3p, and it also has a 3d, which has 5 orbitals, which is something we now have to contend with, that as we move away from the nucleus, the sublevels begin to scrunch and become closer together and overlap. So we're going to place 2 electrons in the 3s, which would be like sodium and magnesium, and then we're going to place 1 electron each in each of the orbitals of the p sublevel, which would be the same as moving from aluminum to argon. Once we've filled the 3p, there is a temptation to start filling the 3d. However, it is envisioned that the 4th energy level has a 4s, which is lower in energy than the 3d. So theory says that we fill the 4s, which would be the same as for potassium and calcium, before we start filling the 3D, which would be similar to going from scandium to zinc. So we go up, 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 up by Hund's rule and fill the 3D. Now that we've filled the 3D, we then have to move to the 4P. So once we move to the 4P, this would be the same as filling in the electrons for gallium through krypton, I believe. So we'd go up, 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 down, down, down. And then once we've filled the 4P, we go to the 5S. Theory says we move to the 5S, and we will start filling the 5S with 2 electrons, which would be akin to placing an electron in for rubidium and strontium. And before we can fill the 5P, we need to fill the 4D. So let's go ahead and pencil the 4D in with its 5 orbitals. I'm just following along with the general organization of the periodic table. So we're going to go up, 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 and then down, 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 down. So now we are actually up all the way to, let's see, when you fill the 4D, you're going from yttrium all the way over to cadmium. The next move is we're going to fill the 5P. 1, 2, 3. And the 5P is akin to filling from indium. Excuse me for 1 second. I'm going to take a peek at my periodic table just to help myself out here, to go from indium all the way to xenon. Okay? Yes, from indium to xenon. So we're going to go up, 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 down, down, down. Once you fill the 5P, then you move back over to the 6S. Theory says you now fill the 6S, and you place 2 electrons in the 6S, which is akin to placing an electron for cesium and barium. But the most interesting thing happens. Before you can fill the 5D, you actually have to fill the 4F. So theory says that the sublevel that's next lowest in energy happens to be the 4F, which holds a total of 14 electrons because there are 7 orbitals. So we're going to go ahead and fill that in. That would be up, 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 up by Hund's rule, down, 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 down. So now we have gone basically from cerium all the way over to lutetium. And once you fill that in for the 4F, then you come back to the 5D, and the next sublevel that we're going to fill in is the 5D, which has 5 orbitals. And that will be like going from lanthanum all the way over to mercury. So we'll go up, 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 and down, 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 down. So now we're all the way to mercury. And our next move is to start filling the 6Ps. But we only need 2 electrons in the 6P, just like here and here. So we're going to go up, up by Hund's rule, and we have just completed the orbital notation, which is very instructive. In other words, at each energy level, you're adding a sublevel. The first level has an S, the second has an S and a P, the third has an S, a P, and a D, The fourth has an S, a P, a D, and an F. The fifth has an S, a P, and a D. The sixth has an S and a P and a D and an F, and so forth. So we're going to write the electron configuration for lead, excuse me. And in doing so, we're just going to follow the scheme from the bottom to the top. We'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I like to write this in the order of the filling of the sublevels and orbitals, 3d10. And then comes 4p6. Then comes 5s2. Then comes 4d10. Then comes 5p6. Then comes 6s2. Then comes 4f14. And then 5d10. And then finally 6p2. That's quite frightening when you look at it, right? It's very intimidating, but in a way you can kind of simplify it, because once you have filled the 5p for xenon, in other words, once you get all the way here to the 5p, another way you can write this as, did I say, yeah, 5p for xenon, you can write xenon. In other words, all of this is equivalent to xenon. Then you have 6s2, 4f14, 5d10, and if you can explain this to anybody on a dinner napkin, you're doing good. You'll amaze your parents and friends. 6p2. Keeping in mind that the definition of valence electrons are the electrons in the highest occupied S and P sublevel. The highest occupied S and P sublevel is the 6s, because we have 6s2 and 6p2. That being said, there is a little time-honored classic shortcut that I'd like to introduce to you. And if you can remember how to set this up, you can remember the order of the filling of the orbitals. I believe this is presented in your textbook. It is a time-honored classic little cheat sheet that students have used. Whoops, this should be 5. Used through the years. And I'll just kind of whip it out here. 6s, 6p, 6d, then 7s, 7p. So the way this works is you draw an arrow going down diagonally in this fashion. So you fill the 1s, which are these 2 electrons, and then you fill the 2s, which are those 2 electrons. And you follow this from the end of the arrow to the arrowhead. You place 6 in the 2p and 2 in the 3s, correct? We did that. And then your next move is to draw an arrow here, and you place 6 in the 3p and 2 in the 4s, which is exactly what we did. Next, we'd follow this to the 3d. We'd draw another arrow just like that. So we'd have 10 in the 3d, then 6 in the 4p, and then 2 in the 5s. Once you get to the 5s, you go back to the 4d. So you draw another arrow right here diagonally, and you place 10 in the 4d, 6 in the 5p, and 2 in the 6s. And then after the 6s, you go all the way back to 4f, and you place 14 in the 4f, you place 10 in the 5d, And in this case, you place only 2 in the 6p, but we know that the 6p will hold a total of how many electrons? It holds a total of 6, and the s is 2, and this should be a 6d, which holds 10, the 5f holds 14, and the 7p holds 6. So you could continue this scheme going on, and we can actually expand our quantum mechanical chart. And if you think about it, there are 2 electrons on the first energy level, 8 on the second, 18 on the third, 32 on the fourth, and then this gets a little bit ticky-tacky. If you total these up, I'm going to stop totaling them because actually you could expand this, and we will do that later. Because notice that you add a sublevel with each energy level. So the next sublevel for the 5th is the 5G. And then the next one here would be, you'd have a 6F, a 6G, and then a 6, what comes after G? H. But for now, we're going to stick with these top 4 rows. And that is the electron configuration of lead, which should demonstrate to you that you can handle larger elements if you follow the quantum mechanical view of the atom and the pattern.